when you don't know about the characteristics of your data, it will happen in many real-time challenges. You'll not be able, you'll have thousands of variables, lakhs and crores of data, right? You'll not know the distribution of your exact data. Then in that case, if you want to do feature scaling, go ahead with normalization, otherwise standardization, if you are sure about the behavior of your data and that it follows a Gaussian curve, right? Now, can you imagine like what will happen in case we do a linear regression with scaling and without scaling? Has anybody tried that in the past, or has anybody tried comparing the results? What will happen if you have certain variables, if you build a linear regression model, one scaling the variable and the other model without scaling the variable? Can you guys, do you have any idea what will happen, or what will your model, how will your model behave? Will it improve or will it not improve? Or will it like improve to a great extent? What will be the consequences? Anyone?
Ma'am,
yeah.
Like if we don't like normalize or standardize the features, independent variable. So if one of the independent variable has scale like 10,000, 20,000 and 30,000, and one of the independent variable has scale like 1, 2, 3. So without doing standardization, it will give great weightage to the scale like 10,000 and 20,000, and give low weightage to the scale of 1, 2, 3.
Okay. So according to you, the model should show, a decline in performance, right?
Yes, ma'am, we can say that.
Okay. Okay. So I in this because we have not very much.
And also, as here in this linear regression, we are dealing with distance between the vectors, as distance between the points is the main criteria while calculating the errors. So if we have a large features with, as someone said previously, if we have a large scale difference, it will be very difficult to measure the distance. So computationally, it will take more time. So if we bring everything to the small, if we crunch those numbers, so it will be very fast, like in calculating the errors and all.
Okay. Cool. So in this exercise, or this hands-on, right? So we'll just try to see or see what happens if we scale the data, if we don't scale the data. We'll try to build two models. So we have a data set called as insurance. We'll be giving this, I don't think so I'll be able to share this here directly, but yeah, we'll be giving you the copies of this notebook as well as the data set. So Sure. Yeah, I'll just quickly cover. Thanks, Rudra. Yeah. So here we have a Sweetwiz library. So Sweetwiz is a beautiful library by Python. So you can install using pip, and what it will do is basically it will kind of visualize or kind of help you in the EDA or the exploratory data analysis of your variables. So see, insurance data I've taken as an example. It has variables like age, gender, BMI, blood pressure, diabetic children, diabetic, number of children, smoker, whether you smoke, whether the person is a smoker or not. So this is like the same medical claim data, right? And the business case which we talked about in the first slide as when we started the workshop session. So claim is the amount of the claim that the person needs to do, right? So these are the independent variables. It has a combination of numerical as well as categorical variables. Now, what we do is we are leveraging the Sweetwiz library here, and we are like giving the target feature. And what does it show? So see, it will give you beautifully you would have heard about describe, right? Describe will give you all these information in a number or in tabular format. But if you want to visualize it further in the form of like very well segregated or neat way, or with the presence of graphs and all, or automatically, you don't need to do anything. No need to separate any categorical or these variables separately and then do describe. You just simply call the Sweetwiz library and then you'll be able to get this kind of EDA. So if you want to, so at Algoritmo's Insta page, you might be, so it's very difficult, right, when to remember all the libraries and all. So in case you want to see what library is responsible for what and what kind of what does sklearn do and all these things. So you can go ahead and visit the Algoritmo Insta page or the LinkedIn channel, and you'll be like getting this kind of informations very frequently. So you can also post or comment in case you are interested to know more about any particular kind of any particular kind of technique or algorithm, right? So we'll try to include that also. Yeah, so now we are doing, let's do first unscaled data, right? So first we'll build the model on unscaled data. We'll not scale the independent variables. Now we will, because we have categorical variables, now we will have to do some kind of encoding in order to convert them to the number format, numerical format. Now you notice here we are doing n-1 dummy encoding on the categorical variables and not one hot encoding. Can anyone tell why? Because because here I'll just move a little bit quick here. So because because it's already 12:36. Yeah. Okay, so why do we go ahead with n-1 encoding and not one hot encoding here? Because you see n-1 encoding, smoker, yes, there were two values for smoker, yes or no, but ultimately in the data you got only one variable, n-1, 2 minus 1, 1. And what would have happened if you would have had another variable called a smoker, no, right? So that variable would have kind of depended. If this is smoker, yes is 1, then this is 0. Smoker, yes is 0. Then
we will again have
multicollinearity.
We will again have multicollinearity. Yes.
Exactly. Yeah. So empirical relation and this multicollinearity will get introduced in such cases. So because linear regression, this multicollinearity assumption is important. So better to have n-1 dummy, n-1 encoding rather than one hot encoding. This is an important practical point which many people don't bother about while building model, but yeah, practically this will affect your model. Now we splitted the data into train and test, and then we train and test as in just to evaluate your model internally, and then we using OLS from stat model library, we fit a model. This time we didn't scale the model, right? As you might remember. See, what did you get as R squared and adjusted R squared? You just take a look at this value. We'll revisit these values once you can maybe note it down somewhere or have it in your mind. We'll be comparing these values with the scaled version when we build the scaled version of the model also. Okay. Now you got this right. Again, one more point to notice, look at the coefficients, 258 age, 319 BMI, 9.1733, right, for blood pressure. Okay, so just have a look at just keep in mind about these coefficients and the R squared and adjusted R squared. Let's move on now. The same thing, now we will build a model using scaling of data, right? Now for scaling, we would we can scale only numerical variables. So we'll have to separate the numerical and categorical variables. And on numerical variables, we will apply standard scalar scaling, right? One thing you notice, we use the function called as fit_transform here. What this will do, and we have a link here which very well describes what this fit_transform versus transform will do. Always in any kind of algorithm or model building exercise, you would want to scale your data with respect to only training data and not including testing. Why? Because training data is something which you have in hand, which you know about, right? As of now, at this point of time. Testing data is unseen. You should not know the characteristics. You should not make your model bias by making it know the characteristics of test data, right? So fit underscore transform, this function, why are we not using just the transform function? So what is the difference between fit underscore transform versus transform? Fit underscore transform will store the mean and standard deviation of your training data, and when it sees the test data, the unseen data, it will apply or it will scale your test data also as per these variables, the mean and standard deviation of the training data. So because you should not bias your model basis the characteristics or the behavior of test data. Test data is entirely unseen. If you make your model bias basis like the test data characteristics, you will get good accuracy, but again your model will not be generic anymore. So always use fit underscore transform and scale your data as per only training data, not the test data. Don't include test data while scaling the model, right? And this link you can follow. Basically, this is a very good link for knowing about the transform and fit underscore transform function. I've pasted in chat also. Now, again, moving back to scaled and unscaled. So what we did here is we again converted this to scale. We scale. Now, one more thing, you will not get the column names once you use the fit underscore transform, right? It converts the results into array. So explicitly, you will have to use the column names of your initial data set and again assign it back to the scaled data version. Now you see all the data is scaled, right? Now, again, we'll do n-1 encoding for the categorical variables. And then we'll do the same process, splitting into train, test, and then fitting a model, and then taking the summary. This version is with the scaled version. What did you see in the R square and adjusted R square?
Adjusted R square is less than R square.
Okay, that's fine. But R square and adjusted R square as compared to the model when we did not scale it. It's same. It's exactly same.
Same.
Yes, right? So surprising, right? So because you as in didn't change information, but so you just scaled the data. So you will get the exactly same model goodness of fit of the model. Although look at the coefficients when you had this unscaled model, looking at this age variable, you cannot say, oh, age coefficient is important than BMI, or children is important than blood pressure. No, you cannot assess that from here just by looking at the coefficients. And here, since you already standardize everything, you can simply say, looking at the magnitude, age coefficient has magnitude which is greater than children or blood pressure for that matter. So it is more important in terms of variable, right? So age is more important as compared to the number of children or the blood pressure. Yeah, obviously there are other terms. So the next topic which already we wanted to cover is model interpretability. So in summary, you will get lot many parameters from where you can interpret about the model correctly. So one is the coefficient. Scale coefficient, obviously you can look at the magnitude and simply greater the magnitude of a scaled version model, more is the importance of the variable. Standard error will allow you to define the confidence. So how much plus or minus the range, what can be the range of this coefficient? So 0.30 plus or minus 0.016 will be the range for your age variable. Okay, so that is how you define the range of that particular variable. T statistics is nothing but coefficient divided by standard error. It measures how effectively your coefficients are being measured. And p-value, again, if you just simply want to look at the importance of any variable, lower the p-value, the more important the variable is. You can see age and BMI are more important than blood pressure. So both the models are important with unscaled, scale, but the purpose is different. Here, by looking at the coefficients, you can directly compare the models. For here, you cannot simply compare the coefficients. For that, you'll have, for checking the importance of the variable, you'll have to look at the p-value. Okay. So an adjusted R square again represents the goodness of fit of your model, and degrees of freedom 1059 is the degrees of freedom here, number of observations. So this is all the how you interpret the summary of your model, right? Going back to again model interpretability, we already covered that in the notebook that we were discussing. Any model, when we try to approach, we get the sample data and then we do the EDA, we do the preparation of data, transformations, data pre-processing, charts, and all plotting, and then design the model. Once you are satisfied with the EDA or the transformations, you design the model that best explains your data. And then you, in order to see whether your model is performing good or not, you evaluate that performance. And you do improve also, right? In case you don't feel your model is performing great, very great, so you just do hyperparameter tuning or any kind of adjustments in the transformations. Again, you do all these kind of steps to increase your model performance. And it should be an optimal model performance, not like it's not like you can get an R square of 1, but it's too good to be true, right? Considering the quality of data in your hand. So always you should not be tempted by looking at more the more the goodness of it, more the model quality, but you have to you should get always an optimal model performance rather than the large model or large values for model, goodness of fit model. Make predictions for the whole population. So from the sample, you are kind of trying to get the characteristics for the population. So that is the whole aim of building the model. Before we move into any kind of next questions, I just want to cover one more important topic here. So there is something called as interaction, right? So in this variable, in this, let's say, what would have happened if BMI and smoker would have been would have an interaction effect. So when interaction, as in, let's say you know, right, a person with more BMI is obese person and is more likely to have more diseases and hence more susceptible to larger amounts of claims. What if the obese person is also a smoker? The combination of smoking and obesity, right, that can all have a completely different impact on the Y variable, right? So if you multiply BMI and smoker and create another variable, right? One second, give me just 1 second. So that is called as interaction, because your BMI and your smoker, those two variables in turn are having an interaction between themselves, right? So that these kind of effects is called as interaction effects. And to give another example, right? Let's say you have you're measuring the growth of a plant, the height of a plant, right? And you have one is like the presence of sun or the ozone, and the presence of bacteria. Let's say seaweed, we put seaweed, right, on plants in order to make them grow healthy and all, right, or grow fast. But these can be two independent variables. But you see, the seaweed plus the ozone or the sunlight, they themselves have an interaction effect between them. So that might cause a separate or a different effect on the Y variable. Okay, so you see here in this this is the same data. This time what we have done, we have all the steps are same, converting the categorical columns to the and one is dummy encoding, splitting the train and test data, and then fitting the model. But here, if you see, we have taken a variable called as BMI smoker. Yeah, now we create a BMI smoker. So we just multiply BMI into smoker, yes, right? Now we again try to fit the model. Now you see the entire R square got changed. It can increase, it can decrease, but it has an effect, right? It had an effect. It got increased. In fact, see, it got increased from, it got to increase to 83%, right? So you can see now BMI and smoker, the interaction between them is more influential on your claims or Y variable as compared to the individual variables taken separately. BMI, smoker, yes, separately they have some more effect, but BMI, smoker, see the value and the coefficient, right? So this is called as interaction. Now, last but not the least, the most important thing, why we call the OLS estimators as BLUE, right? Best linear unbiased estimates, because of the very nature of the OLS. It tries to fit the best, in whenever I say best, it means the optimal. So optimal parameters it tries to fit here. Those are linear estimators and unbiased. Now, since we have been talking about the beta coefficient in terms of matrix notation, right? E to the power E transpose of E, square of error, right? In matrix, how do you represent square of a matrix? X transpose of X, right? So what is your X, what is your E term here? Actual minus predicted. Y minus X beta, right? You substitute that value of E inside these equations. When you solve for that, you and you solve for that again, you the next step is to differentiate that and equate it to 0, right? Equate the matrix to 0. You will get this entire equation of beta, which we have been seeing for a long time, right? Beta equals to X transpose X inverse into X transpose of Y, right? This one. So this is the OLS estimator. This is what you called as estimator, right? This is what you were estimating. Now, when these error terms, as you already know, must follow the Gaussian Markov model, right? So for Gaussian Markov model, for normality, right? So Gaussian Markov model has these conditions. Error, the mean of the error or the expectation of the error term should be 0. There should be constant variance, and there should be no autocorrelation. The constant, the dependency between the error terms should not be there, right? So constant variance, mean should be 0 now, and there should be no autocorrelation. These are the standard terms of standard Gaussian models. That's why we said in the initial basis, this only we have our assumptions, right, for linear regression. Now, why do we say BLUE estimators best? Because it obviously identifies the best parameter, best meaning optimal, the local minima. Why is it unbiased? Because in this equation, if you try to, so expectation of beta OLS, right? Beta from OLS. If you try to solve this equation, right? So what is beta OLS? X transpose of X inverse into X transpose of Y. Now, Y in the second equation, in the second, I mean to say here, let me annotate this. So yeah, here we just simply substituted the value for Y. And we kept solving this, right? So you will ultimately reach here, error of beta, expectation of beta OLS equals to expectation of beta plus X transpose of X inverse S transpose into expectation of error. Now, due to Gaussian model assumptions, standard Gaussian Markov model assumptions, this will be 0. So something into 0 plus beta. So E of beta OLS, whatever beta OLS gives you, that is the best beta, or that is the biased beta, because E of beta OLS equals to beta. So that means it is giving you, and this is the proof that you from OLS you get unbiased beta. This is not something like beta OLS equals to like beta plus some term E, some term C. No, right? This is exactly beta OLS is coming exact equal to beta, right? Considering we have the condition error, expectation of error equals to 0, that Gaussian term. So only this, because of this condition, we get true coefficients or unbiased estimators. That is the concept behind blue. That's why we call it as blue, best linear unbiased estimators. So variance is same for all observations, homoscedasticity, errors are unbiased and low variance, and there's no autocorrelation between them. Okay. I might have gone a little bit fast at the end, but yeah, we'll stop here because this kind of marked the end of the session or workshop. Hope you enjoyed it, but let's open the floor for questions, comments, thoughts, anything. Anyone would like to share their thoughts or comments, please feel free. And also one more important thing, there is a chat. I'll be posting the link of the feedback. Rudrava, if you don't mind, could you ping that to everyone? The chat, the link for the feedback. So please feel free in case, whoever is interested in participation certificates and any more further updates about this. So please fill out this survey or the feedback form and yes. So any books that we can suggest. So there are many books. So it's all again like there are Springers, there are books about linear regression in specific, or there are books which cover all the concepts of data science, like at least the machine learning, the mathematical models at least. So Springer or O'Reilly publications, all these things you can find on internet. Even if you try to study, right, it's just not depends on the book, it's how you interpret them. So simple videos, short videos also, if you get, just try to question those things, right? Like why those assumptions. We will in the books also we'll be able to get all these assumptions mentioned, but why those assumptions? Why no multicollinearity, right? For example, why no scaling? What happens if I do scaling like this, if I do scaling like that, right? So all these things you might not be able to get in like many books for that matter, but yeah, you might need to look or ask questions or discuss with different people, right? Why this assumption? Why this particular concept? Please keep workshops on feature engineering, machine learning, pipeline, ML model deployment. Surely we'll see. Anyways, if even you are interested to see about these, keep looking for the updates in our Instagram channel, Algoritmo Instagram channel, and also the LinkedIn platform, LinkedIn channel for Algoritmo. Please subscribe. Please look at the content over there. Yeah, the links I think Rudrava has posted here just now. So you can go ahead and take a look at these links. And obviously we'll be organizing much more in many more workshops. Deepan, Rudrava, you want to pitch in? Anything else you want to say?
Yeah, Sonam, they have to, all the participants need to fill in the feedback form.
Yeah.
And the certificates will be mailed accordingly. So please ensure the name of the spelling and the email IDs are entered correctly in the form. Am I audible?
Yes, Deepan, I can hear you. Okay, so please take 5 minutes of your time, fill this form, correct IDs, so that we can update you about any upcoming workshop or anything. We can interact over email also. Okay. Any more questions, thoughts, comments? How did you like this workshop? What was your thought about this?
I would also like to add one more point to everybody who is attending this workshop. Like, please do invite your friends and colleagues. More participants joining this kind of workshops, we will also be motivated to organize such workshops again and again.
Definitely, it is good to have more and more participants here. So feel free to talk about this with your friends, amongst your friends and colleagues, and whoever are data science enthusiasts. Oh, so Himanshu says he didn't know earthquake can be negative. Yes. So that's what our aim, basically, to ponder on the things that we really don't care about in real world, right? So thanks everyone for the feedback, and looking forward for your feedback on the link which Dipine and Rudrava had sent, and we'll be sending the participation certificates over email. Thanks everyone. Thanks.
Thank you, Swarna. Thanks everybody.